In this video, we're going to look at the divergence theorem. We're going to explain what the divergence theorem actually means. We're going to use the divergence theorem to calculate the flux of a vector field, and then we're going to apply the divergence theorem to an electrostatic field. We are now in Calculus 4. We're at the tail end of vector calculus. This is the last thing we're going to learn in this class and in vector calculus for this class. So let's just wrap up where we've been and where we're going. The first thing we learned in Calculus 1 was the fundamental theorem of calculus. And whether it was with respect to x, so as dx, or with respect to y, dy, we were going along some sort of curve that was going along with the x or the y-axis. And that's really good if I'm only wanted to be the x, y, or in z if I wanted the z-axis. Then we went into the fundamental theorem of line integrals. And that allows us to talk about curves not going along the x-axis, y-axis, or z-axis. So the fundamental theorem of line integrals is the more general form of the fundamental theorem of calculus. Then we went into Green's theorem, which is talking about the circulation over this vector field in reference to this vector field F in reference to some region D that we were looking at for circulation. So Green's theorem is only in two dimensions, whether it is circulation or flux. And when we're talking about the circulation or flux with Green's theorem, we are talking about what's happening over a vector field, and in particular we're looking at some region D and not just a curve in space. We're talking about what's happening along this area. Stokes' theorem, which then goes to a higher dimension. Stokes' theorem is like the easier version at some point, or the more generalized version of the curl, which is Green's theorem for circulation. So you could say Stokes' theorem is the generalized form of Green's theorem for circulation, which means that the divergence theorem is the generalized form of Green's theorem for flux. Now, Green's theorem is only in two dimensions, and Stokes and the divergence theorem is for higher dimensions. And so what is the divergence theorem? Well, the divergence theorem basically is that I can go up to three space or higher, or I can go down to 2 dimensions. Just depends on what is the most appropriate thing to do. So we are now looking at the triple integral over this solid region E of the divergence of this vector field dv is equal to the surface integral along the surface of this solid, of this vector field dotted with a ds. So there's a couple of things that has to happen, is that it has to be piecewise smooth. So here's a picture. I've got this solid that is piecewise smooth. The surface is piecewise smooth, and then the solid, of course, would be a solid. We assume that it's piecewise smooth closed surface that encloses some solid E in space. We also assume that S is orientated outward, so we're assuming that all of our normals are moving outside of our solid, not pointing inside of our solid. And F is our vector field with continuous partial derivatives on this open region containing E. Then this is true. So my divergence, or the triple integral over the solid of the divergence of F dv is the same thing as the double integral of the surface integral, the sum of the surface integrals, I should say, of F dotted with a ds. So this allows us to go from one to the other. Now, I'm going to look at this first example, and I want to talk about what's going on with the divergence, and then what's going on with the, if I were to do this as separate surface integrals. So first I'm going to use the divergence. And the divergence, and this is going to be long, and I'm going to have to erase a couple of times to show you that I'm going to get equivalence, whether I was to do each side of this cylinder, which is the top, the bottom. So I'm looking at a cylinder. Here's my cylinder. It has a top. I call this the top. It has a bottom. And it has this side. It's like a tin can, if you will. So the divergence theorem says that I can find, let F be this vector field, S is a surface bounded by the planes, and I want to find this surface integral. And I'm going to use the divergence theorem first. So the divergence theorem is this triple integral over this solid E of the divergence of F dV. Now F is a vector, the V part of dV is not. Okay, so what do I need? Well, I need the divergence. So remember from previous videos that the divergence of F is the vector that is formed by taking the partial derivatives. This is P, this is Q, this is R. So the first position will be P with respect to X, Q with respect to Y, and R with respect to Z. So the divergence is going to be 3x squared, 3y squared, and then just 3a squared. Okay, so we found the divergence. Now what I have to do is I have to figure out how I'm going to relate this divergence and this surface that I'm being bounded by. So I'm going to use the parameters that we're usually using, which is I'm going to say x is equal to r cosine theta, y is equal to r sine theta, and of course z is equal to z. So I'm looking at this cylinder, and I see that z is going to run between 0 and 1. That's z. R is going to run between, so R is going to run between 0 and a, because that's the radius of our cylinder. And theta, of course, is going to run between 0 and 2 pi. Now, I have to parameterize my divergence in terms of my x, my y, and my z. And so this divergence is going to be equal to, well, you notice each one of these terms here inside this vector has a multiple of 3. So I'm going to pull that 3 out front. So I'm going to do this 3, and I'm not going to decide how I'm going to do the order, but I am going to need an r dr, a d theta, and a dz, because that'll be the volume, right? Because we parameterize in terms of r sine and r cosine. So I'm cylindrical, so that means I need to always have that r dr dz. We could talk about the Jacobian that produced that in other videos. We've talked about it in class. Okay, so I needed to do the divergence in terms of my parameters. So the divergence of f in reference to my parameters, which is r, theta, and z. This is going to be equal to, I pulled the 3 out, so I don't have to worry about that. This is going to be equal to, let's stop a minute. Divergence is not a vector. Divergence is just the sum of this. So let me erase this. Probably thinking, what is she talking about? It's not a vector. It's just going to be the sum of those partials. There we go. So I have a replacement, 3 got factored out, and I have a replacement for x, and that's going to be r cosine theta, that's going to be squared, plus a replacement for y, which is going to be r sine of theta, the quantity squared, and then I don't need a replacement for the z because there isn't any z there. So that is 3 times my divergence. So you can see I pulled the 3 out already. So up here, I know I'm going to have r squared cosine squared theta, r squared plus, man, what is it with my positives and negatives and additions today? So plus r squared sine squared theta plus 3a squared dv. And again, I have not decided on how I'm going to do the order yet, but the order will be something in where I've got to have an r, dr, d theta, dz type of thing. Okay. Now, we know that if we factored out an r squared out of those two terms, I'm going to have a cosine plus sine squared. So we have 3, the triple integral over this solid region E, and then I'm going to have r squared plus 3a squared dv. Now, it doesn't really matter the order and how you do this. I might do my r first. It doesn't really matter. So I have 3, and I have this double integral. I'm going to do z last, so I'm going to go from 0 to 1. I'm going to do theta second, so it's going to go from 0 to 2. I'm going to do r first, so I'm going to go from 0 to a. And so I have r squared plus 3a squared, and then I need an r because remember we talked about the Jacobian and needing to have that r dr d theta. So I have r dr d theta dz. And when I get totally done, I'm just going to skip to what it's going to be. It's going to be 9a squared pi over 2. Now, we did this with the divergence theorem, right? We didn't have to do each individual surface. We did it right to the divergence theorem, and that's our answer. So I'm just going to put this answer over to the side. So 9a squared pi divided by 2. Now I'm just going to erase this. And the reason I'm going to erase this is because by the divergence theorem that I could have done it by each individual surface, right? I can do a bunch of surface integrals and I should get the same answer. So let me see. I don't know why that is okay. Let's move that here and let's lock that down. Okay. I'll lock that right there. Okay, so now what I'm going to do is I'm going to do this by each surface. So again, what I have is this cylinder, and I have this surface in which z is equal to 1. I have this surface in which z is equal to 0, and then I have the sides of the cylinder. So I know that the surface integral, so I have the first surface, so surface 1, f dotted with ds, plus surface 2 of f dotted with ds, plus the third surface, surface 3, of f dotted with ds. Now, f is a vector, and so is ds. So let's assume the bottom part is surface 1. So I've got the bottom, we'll call surface 1 is the bottom. Okay. So with surface 1, I'm going to call the bottom, and with the surface 2, I'm going to call the top. And with both of those, I'm going to parameterize the same. I'm going to have r. The only thing that's going to be changing here is the r and theta. So I have r and theta. And z will be z. So r of theta is going to be r cosine theta, r sine theta, and then z, which is z. And then I'm going to do r, I'm going to do t with respect to r. This is going to give me r, or excuse me, it won't be an r, it'll be cosine theta, sine theta, and 0. And I'm going to do t with respect to theta, tangential, which is a partial derivative with respect to theta. And so that's going to be negative r sine theta, r cosine theta, and also 0. T r crossed with the cross product with t of theta is going to be equal to, the first one is going to be 0, the second one is going to be 0, and then the third position I'm going to end up with, let me see, it'll be r cosine squared, so it'll be r cosine squared theta plus r sine squared theta, which we know if we factor down an r, I'm just going to get r, because sine and cosine squared is 1, so I'm just going to get r. All right, so for my top surface, when I do t, actually let me just do t of r crossed with t of theta and its dot product with f of r theta. So I go and I do my replacements with r and theta, and z is z, right? So when I do this, the only thing that's going to end up, because I have 0, 0, and r, is going to be this third term. So when I do this dot product, the only thing that's going to show up is this third term. So this is going to give me 3a squared z r. Now, so my first surface, when S1 is on the bottom, that tells me that z is equal to 0. So then that 3a squared z times 0 is 0. And so for this vector, for that surface with a normal going in that direction, it's going to be 0. When I'm looking at my second surface is the top, that's when z is equal to 1. So I'm going to give 3a squared multiplied by 1. So I just have 3a squared. All right, now I'm ready to do the integral. So I'm going to do this integral, and it's going to be 3a squared r dr d theta. Because don't forget, I'm doing r dr d theta. So even though there wasn't an r there, actually there should have been an r there. I dropped an r. So let me go back. And this should have an r. This should have an r right here. This should have an r right there. Okay. So now I'm ready to set up my integration. I'm going to have 3a squared r. I'm going to go from 0 to a in my r, so I'll do dr first, and from 0 to 2 pi d theta second. When I get totally done here, I'm going to get something like 6 pi a to the 4th over 2. In other words, I get 3 pi a to the 4th. Okay, so I'm just going to pay attention to that bit of information. Now, the next one I'm going to do is the cylinder itself. So I'm going to pay attention to that. I'm going to do the cylinder itself. And when I do the cylinder itself, I'm going to parameterize like I've done a bunch of times, and I'm just going to say that I'm going to parameterize with r of theta and z. And so this is going to be no surprise. It'll be a cosine theta, a sine theta, and z. And then when I do t of theta crossed with t of z, the end result is going to be the cosine of, it'll be a cosine theta, a sine theta, and then it will be 0 right there. All right. So now when I find my f of r of theta z, this is going to be equal to, replace x appropriately, will be a to the third cosine to the third theta, a to the third sine to the third theta, and it would be, of course, 3az, a squared z. Okay, when I do the dot product of this, and I do a study ready to start my surface integral over the surface 3, when I do my dot product here, I'm just going to end up with 3, well, I'll have a to the 4th, excuse me, not 3. It'll be a to the 4th cosine to the 4th plus a to the 3rd, a to the 4th again. Man, a to the 4th cosine sine of the times. The sine to the 4th of theta, and then I'll have d theta dz. Cool. So that means I need to figure out what my limits of integration are. I decided to do theta first, so I'll go 0 to 2 pi, I'm going to go from 0 to z is going to go from 0 to 1. And when I get done with this, I'm going to get 3a squared pi over 2. Now, if I add these two together, I will get this right-hand side. So was it faster to do the divergence theorem? Oh, heck to the yeah, right? Go heck to the yeah. Can I always just jump to the divergence theorem and ignore the left-hand side? Mostly. In this next example, if I were to do that, if I were to ignore the left-hand side in its entirety, I would get the wrong answer. Well, why is that? Well, because I have this hemisphere. So I have this hemisphere, and it looks something like that. My drawings are the best. Should probably do AI to do my drawings. And then I want this vector that is on the xy plane, and I need the unit normal vector there. And then I would have all of these vectors coming out of this. And I want to calculate this. So the surface I really care about is the upper hemisphere. However, I do have to think about the disk that's formed on the bottom part. So what I'll end up doing is I will have the double integral of the surface of the sphere, so we'll call it S1, of f dotted with a ds. And this is what I want. But then I also have the surface integral over the surface 2, which is, I'm going to call this the bottom, I'm going to call this S sub 2, and this S sub 1. And that's my want, and my want is S sub 1. Let me put it in different colors so it doesn't muddy our waters here. This is the S1, that's my want. The bottom disk here is S sub 2, and I'll need that. And I'm going to have an F dotted with a ds, and it's going to be equal to the triple integral over this solid region E of the divergence of f dv. Now, I have the right-hand side, so let's go ahead and find the divergence. So again, this is P, this is Q, this is R. So the divergence of F is going to be equal to, it will be the vector, no, it won't be a vector. Why do I want to call it a vector? It's going to be the derivative of P with respect to X, which is 0, P with respect to Q, or Q with respect to Y, which is 1, and then Z with respect to, R with respect to Z, which is 1. So we just get 2. Oh, that's lovely. Why is that lovely? Because this triple integral over this region E is just going to be 2 times the volume of the shape. Well, the volume of that shape is half of a sphere. So I just have to figure out what the volume of a sphere is and just take half of that. And then lo and behold, I can skip a good share of the work on the right-hand side. Now, can I skip the left-hand side? The answer is no, but man, it would be nice if I could. And so if I skip the, just going right to the right-hand side, this right-hand side is just going to be equal to 2 multiplied by 2 pi over 3, and then multiplied by its radius squared, which is 1 squared, and so this is going to be 4 pi over 3. Now, I do have to deal with this piece, because my want, remember this is my want, so I'm going to have to parameterize just that one piece, that one surface, and then I'm going to subtract it from the other side, and then I'll have what I really want. Okay, so how am I going to do that? Well, I'm going to start by looking at what I have, and I basically have a disk on the XY plane. Okay, so because of the fact that I can go right to, by the way, I know that F dotted with a ds, in this case, on the surface, is going to be, well, ds is just going to be the vector in that direction, and the vector in that direction is straight down, so that's just going to be negative k. So that's kind of nice. So that is going to be negative k, and then what do I have left over? Well, I have left over dx and dy. So those are the things that are left over. So I can just go right to my integration. So this is equal to the double integral over this disk D of negative, so what's the last thing? Oh, this is the thing that I get. And so the only thing that I have in the k direction is, the only thing I'm going to do when I do the dot product is going to be this. And so it's going to be the negative k and this, so it's just going to be negative, it's going to be negative z minus 1. But, and then dx dy. But here, z is equal to 0 because I'm on the disk, right? This is where z is equal to 0, is right on this disk. And so if this thing equals 0, then this integral goes on this disk D of just 1 dx dy. Well, that's kind of cool. So do I need to parameterize? Well, I can, but I don't really need to, because what I'm doing is I'm looking at this circle, right? And so I can say that my x is going to go from negative 1 to 1, and I'm going to say that my y is going to go from the square root of 1 minus x squared, the negative of it, and then the square root of 1 plus x squared. When I get totally done with this, by the way, I'm going to get just pi. But I didn't even have to do any of this, right? Why did I not have to do any of this? Well, because the dA is the area of this disk. And the area of this disk is pi r squared, where r is equal to 1. Okay, cool. So what my want is, remember, I'm going to come back over here, and what my want is to find out what the double integral of the surface of the upper hemisphere of f dotted with ds is equal to. Well, this is going to be equal to the triple integral over this solid region E of the divergence of f dv minus, in this case, it's going to be minus the surface of the disk, f dotted with ds. And so this is just going to be 4 pi over 3 minus pi, and my answer is pi over 3. And there is my answer. For part B, this is just a box with those vertices. And because it's a box with those vertices, I can go right to the divergence theorem, and I'm going to use the divergence theorem. And it's going to be lovely. And I'm going to say, hey, I'm going to do the triple integral over the solid region E of d, the divergence of f dv. I'm just going to make sure I got my orientation right, which it probably will be okay. So the first thing I'm going to do is find my divergence. So remember, this is P, this is Q, this is R. The derivative of P with respect to X. This is going to be 2xz cubed. The derivative with respect to, and for some reason I just keep wanting to do this as a vector. My mind is on vectors. So this is the divergence of f, and this is going to be equal to 2xz cubed plus 2xz cubed. Oh, this is looking lovely. Plus 4xz cubed. Oh, that's lovely. This is just going to be 8xz cubed. So then this is equal to, and it doesn't matter your order. You can do z first, you can do z last. Let's do z last. And so z is going to run between negative 3 to 3. Y is going to run between negative 2 to 2. X is going to run between negative 1 to 1 of 8xz cubed. Dx, dy, dz. And this lovely thing will end up, when I get totally done, of 0. So at least I don't feel bad about doing a lot of work, because the answer is 0. So let's take a look at our next example. We have z, the tangent inverse of I, of y squared I, z cubed, natural log of x squared plus 1 in the j direction, and then z. where S is a part of the paraboloid that lies above the plane Z is equal to 1 and orientated upward. Good news and bad news. Good news is that, when we do our divergence part, it's going to be lovely, right? It's going to be pretty sweet. The bad news is that I'm going to have to do like I did on my previous example, which means I'm going to have to break it up into two pieces. So first I'm going to do the divergence of f dv, and this is a vector, or actually I'm going to call it d, because before we used dv, is that way, dv. And then I'm going to have to subtract off, right, that surface integral. Well, what's the surface integral I'm going to subtract off? Well, I'm going to be subtracting off that disk, right? So I'm going to be subtracting off that disk that's being formed. So, and how do I know it's a disk? Because if I were to graph this parabola where z is equal to 1, that surface is a disk. And so I have the surface area, and I'm going to do f dotted with n in the appropriate direction, ds. And when I get totally done, by the way, my total answer, when I get totally done with everything, is going to be 3 pi over 2. Now you're wondering, why aren't I working this all out? Well, at this point, I'm hoping that you have had some experience with doing surface integrals and doing the parameterization, and the divergence is pretty sweet. And also, this video is going to be super long if I don't start just kind of making it a little bit smaller. All right. What about this next one? Use the divergence theorem to compute the flux integral, where f is this, consists of the unions of these paraboloids, and this disk oriented outward was the flux through just the paraboloid. Okay, so guess what? This is one where I can just do the divergence, which is going to be lovely. So I'm just going to do the divergence of f dv, where f is the vector. So I'm going to do the divergence of f first. And p is 0. It's because I don't see an I, so I have p of 0. And then I have plus j, the q with respect to y, which is 1, the k with respect to z, which is 1. That's 0. Oh, done. Done. This is 0. Isn't that lovely? That was kind of lovely. It was so lovely. Okay, let's take a look at our next example. So the flux of the water through a parabolic cylinders from here to here, where the velocity vector is given as this, that is my v. I want to compute the flux of the water. And so what does this really mean? Well, this means how much water is going through this surface area, or this surface being the y is equal to x squared. So I really want to know how much water is flowing through with a vector field is describing the flow of water. Okay, so good thing is, once again, I can just jump to my divergence formula, because what I want is the flux, which means I can just do the divergence of f dv. So my divergence of f is equal to, it's a 0. That's kind of nice. Wonder if this one's going to be 0 too. That'd be nice, wouldn't it? And then 0, and then, that's unfortunate, it's going to be 6x. But not bad. Okay. So this is one in which I don't have to do parameterization. So I'm just going to have this triple integral of e, and that should be e up there, of 6x dv. So this is going to be, x is going to, z, we'll start with z. And z is going to go from 0 to 3. So we're going to do z last. Y is going to go from 0 to x squared. So I'll have to do x next. So x is going to go from 0 to 2. y is going to go from 0 to y squared of 6x dy dx dz. And when I get totally done, my answer is 72. Not quite as good as 42, but 72 isn't too bad. We have real applications, application to electrostatic fields. It's sometimes easier to think about what we're doing as flow of water, but this could also be the flow of electrons. So let S be a connected piecewise smooth surface, where f of r is equal to 1 over r squared, x of r, y over r, and z of r. Then the surface integral of f, the vector f sub r dotted with a ds is equal to 0. If it does not have the origin, if the surface does not have in the origin, and is equal to 4 pi if it does include the origin. So in other words, this theorem says that the flux of f over r across any piecewise smooth closed surface depends on whether the origin is inside of S or outside of S. And that's it for this video. Could have been longer. You didn't want it longer. I didn't want it longer. We'll talk more in class. We'll see you then.